Hello and welcome. In this tutorial, we're also going to have another hands-on with regards to convolutional neural network. Okay, so previously we have seen one convolutional neural network, and we have had a hands-on on that. Okay, now in this tutorial, we're also going to see another hands-on with regards to convolution. Okay, with regards to convolution or convolutional neural network. Okay. So what we're trying to do over here is that we're trying to give you more hands-on. Okay, we're trying to give you more understanding of the concept that you have done, that you have studied so far. Okay, the more you do, the more you get to understand the concept. Okay, so we're trying to give you different variants of the code or different variants of the lab session, so that one thing that we did not do in one lab session, we can do it in another lab session, right? And you get to know quite a lot of things. Okay, so that's what we're going to do in this particular tutorial. Okay, all right, so let's get started over here. We're going to use another version of the MNIST dataset that we were using earlier on. Okay, earlier on we were using MNIST dataset, which consists of numbers or digits from 0 to 1, right? Handwritten digits from 0 to 1. Now what we're using over here is also called fashion MNIST. Okay, fashion MNIST. This one consists of dataset of fashion, right? Fashion clothes. Let me put it that way, right? Clothes of images of clothes. Okay, it's cloth or either cloth or shoe, right? They are all fashion. Okay, so we have 70,000 of them. Okay, 70,000 of those fashion products, right? They are 28 by 28 grayscale images. Okay, and they have 10 categories, right? And 7,000 images per category. All right, now in training the model, we're going to use 60,000, right, images, like we did in the MNIST digit. Okay, and then we're using 10,000 images for testing. All right, so I mean, this is how this fashion data set looks like. Okay, this is how it looks like in a broader overview. We're going to see some of the things that are inside there in this data set. Okay, so over here, this is what I'm doing, right? I'm importing the libraries as per normal. Okay, I'm importing the libraries for you to see. And one thing that I should also point out over here is that this kind of code takes a lot of time to run. Okay, so if you're running it in your machine and it's taking time, especially when you're doing the fitting part, right, it's going to take quite a lot of time to run, right? So if it takes some kind of a time, you should be patient and then wait for it to run, right? This is computer vision task. It's not the ordinary machine learning where you just run and you go. This one takes a little bit of time to process images. Okay, so you should give it a time. So for instance, in this notebook, I'm not going to run it because it's going to take quite a lot of time to run. Okay, so in order to make the video short for you, I'm not going to run it, because if I'm to run this notebook, I need to wait for some time. Okay, maybe run it, wait for about 15 minutes, especially at the fitting stage. Wait for about 15 minutes for it to run before I continue, which will extend the length of the video, right? But in your own time, you can just give it time and then you run it. Okay, you can just run the notebook and everything will be fine for you. All right, so I'm importing the various libraries that we're going to use over here, right? And then here I'm loading the fashion MNIST dataset. Okay, so you can see the same way that we do MNIST, right? So previously we were just doing MNIST underscore load data, but this one is a fashion version of that dataset. So we do fashion underscore MNIST dot load data. All right, then we store everything over here in the S train and the Y train, right? So here I'm just calling it train X and then train Y, test X and test Y, just the same thing. All right, and then I'm also analyzing the data over here to see, I mean, the shape of the data. Okay, so we have 28 cross 28, right? And then we have 60,000 of those images over there, right? And that is for the X train, right? And for the Y train, you see that we have 60,000 over there. The same way for the testing data, we have 28 cross 28, right? And we're using 10,000 of those images for testing, right? And for the Y test, we are using 10,000 of that for testing, right? Okay, now what we're going to do is that we're going to now find the unique numbers, right, that are there, right? And these are numbers ranging from 0 to 9 digits. Okay, right, so in total you're going to have 9 outputs, right? That is 0, 1, 2, 3 all the way to 9. Okay, that is the label that we have given to the various fashion products that we have over there. Okay, All right, so I'm just going to plot some of them here for you to see how they look like. Okay, so I'm setting the figure size to be 5 by 5. Then I'm going to use subplot. Okay, that is 1 row, 2 columns, and then at the first position. Okay, that's what I'm doing over here. So if you see the image that we have here, right, we only have 1 row with 2 columns, right, and then at the first position, this is the image that will come, right, and then at the second position, this is the image that will come. Just 1 row with 2 columns, right, and then the second position, that's what I'm putting the second item over there, right. So here I'm just going to select the first item. Okay, the first item, and the size is just the same, so I just put it over there that I want all the size, that is all the length and the width of that image. Okay, and the color map is gray over there, right, and that's what I'm doing. And then I map it with the corresponding label that I have in the Y train. Okay, if I pick the image in the S train, I map it with the corresponding label that it has been given in the Y train. Okay, and I'm doing the same thing also for the next image that I want to select in the test data. Okay, so I'm selecting this one in the train data, and I'm selecting this one in the test data. So you can see that in the train data, all right, we have this one looks like some kind of an ankle boot over here, right, and then we have given it a label of 9. Okay, so all those ankle boots, right, they have been labeled as 9. We can have different ankle boots, right, but they're all labeled as 9. Okay, we can have also different types of a shoe there, and then we can give them a different label. We can have maybe a top, we can give it a different label. Okay, we can have, say, a sneaker, we can give it a different label. Okay, if for instance I'm just going to try to run this thing again, but after that I will not run this code again because it's going to take a little bit of time. But I want to show you different kinds of images that we have, or fashion products that we have. Okay, so here I'm going to change it, and then I'm going to show you maybe the product at position 10, right, something like that, at index 10. So let me show you. Okay, you see that it's kind of a top, right, a lady's top over there, right, and the label is 9 over there, right. Actually the label shouldn't be 9. I should change this one to match it, to match the corresponding label over there in the Y test and the Y train. Okay, so now let me do it again. Okay, so the label is actually, see this one, this dress, right, the label is 0, and then this kind of a top, right, it looks like kind of a top, the label is 4 over there, right. Let me try to search for maybe at item number, say let's say at 4, position 4. Let's see. Okay, let me run it and see. Okay, so it looks like something like this, right. This one too looks like the dress that we saw earlier, so you can see that the label is the same, right, and this one too looks like a top, right, the label is 6 over there, right. So I mean, you can just search for the different items that we have over there, right. You can just search for them over there. Here we use I was just wanted to see the first item, right, that's why you were seeing 0 over here. So I mean, in your own time you can do it, right, in your own time you can just do it. So let's continue over here. So here I'm just going to reshape it, right. I'm just going to reshape it from just this, right, 60,000 28 cross 28, like we were seeing earlier, right, 60,000 28 cross 28. Okay, because if you're going to feed it into the convolutional neural network, you need this kind of a shape. Okay, you're going to need this kind of a shape where you need the total number of samples, the height and width, right, and then the number of channel. This one is a gray image, so we have 1 channel over there. Okay, and the same thing for the test, right, the S test or the test X, right, whatever that you want to call it. So I need to do that kind of reshaping over there, right. Then I normalize it over here. Okay, I normalize it over here. So let me just do like this, right. I just have to normalize it. So okay, so that, as I said in the previous video, since it's a gray image, the pixel values are going to range from 0 to 255. So we don't want some values to be very high, some values to be very low. We normalize everything from 0 to 1, between 0 and 1. Okay, that's what we're doing over here, like we saw in the other video. The same thing pre-processing that we're doing, right. We are doing that to underscore categorical over here, so that we'll be able to use it when we go to the cross entropy over there. Okay, I mean the categorical cross entropy, we'll be able to use this test over there to make the probability predictions over there. Okay, so those are the things that I'm doing, right? Then after that, I split it to a train X and the validation X, because I want validation data to be used later. Okay, so in the training data, right, in the training data, I'm also selecting some validation data out of that, which I will use later. You can ignore this step, and then when you go to the fit part, you can just specify validation underscore size to be some size that you want, right? Some percentage, right? 0.3 or something like that, as we saw in the previous video. So you can specify the the validation data explicitly here if you want, or you can do it later on when you go to the the fitting method over there. All right, so we're going to start to build this CNN architecture. Okay, so let's see how we're going to do it, right? So this how it's going to be. We have our image, which is 28 by 28. Okay, and then we've converted this image, right? We have rescaled it between 0 and then 1. Okay, and then we have reshaped it to 28 by 28, and then by 1, which is the channel over there, right? Now what we're going to do is that in the first layer we're going to have 3 by 3 filter over there, right? And we're going to have 32 of them. Okay, like we did in the previous video, we're going to have 32 of them. And then in the second layer we're going to have 3 by 3, and we're going to have 64 of those filters, right? And then in the third layer we're going to have 3 by 3 filter, and we're going to come up with 128 feature maps. Okay, feature maps. So if we start with 32, we're going to come up with, right, it's just going to be something like this. Okay, we have our 3 by 3, right? Our 3 by 3 filter. Okay, our 3 by 3 filter. So let's say this is how it looks like. Okay, 3 by 3 filter. Okay, now when we do when we place this one, right, on our 28 by 28, right, on our 28 by 28 image, we're gonna come up with, remember we have 32 of these 3 by 3, so we have 32 of these 3 by 3. Okay, 32 of them. All right, 32 of them. So here we are not using just one kernel. Okay, so if it's just one, we can just call it kernel. Okay, let's call it kernel, right? And then all of them put together we call it filter. Okay, all of them put together we call it filter. So we have 32 of these 3 by 3 kernels, right, put together to form filter. Okay, now in the first layer, that's what we have. If we go to the second layer, it's going to be the feature map that is going to come up, right? It's also going to come up with each one of these kernels are going to come up with their own feature map. Okay, they are going to come up with their own feature map. This one is also going to come up with its own feature map. Okay, this one is also going to come up with its own feature map. This one is also going to come up with its own feature map. So we end up having 64 of them. Okay, 64 of them, right? Because it's going to be double. Okay, it's going to be double the size. In the same way, this one too is going to be double. Okay, it's going to be double in the next layer. That's how it's going to be. Okay, you start with 32, it doubles up to 64, it doubles up to 128. Okay, all right, so that's what is going to happen over there, right? And then we also add some some pooling over here with size 2 cross 2. Okay, so this is how the architecture actually looks like. Okay, this is how it looks like. So we're gonna start with our 28 cross 28 cross 1 image, right? Input image. Then in the convolution we have 3 cross 3 filter, which is 32 of them. Then we will have a pooling, max pooling over here. Okay, we have max pooling over here. After the max pooling, we do again 3 cross 3 filter, right? And in this case it's gonna be 64. Okay, 64 of the filters over there. And then again, right, we do max pooling. Okay, 2 cross 2 max pooling over there. And when we do that, we're going to come up with another convolution layer over here, which is going to contain 3 by 3 filter, which will have 128 of them, right? And then we will have another pooling on top of that, 2 cross 2 pooling, right? Then finally, whatever output that we have here, right, we flatten it to one long array over here. Okay, one long array over here. Okay, so whatever that we're going to have output over here, right, it's going to be in the form of a matrix like this. Okay, so we need to convert that to one long array like this so that we can feed it to our neurons over here, right? They will become data points that we can feed it to our neurons over there. Okay, and then we can now continuously use the fully connected. So after that, then we come to our dense layer, which is the fully connected with 128 neurons over there. Okay, and then finally we have 10 units, which is because we have 0 digits from 0 to 9, which is 10 digits. Okay, so we need to have 10 units over there. Okay, so here we're going to have soft max. Okay, we're going to have soft max over here, right, for that final predictions over there. Okay, so that's how our architecture actually looks like. So here what I'm doing here is I'm going to specify the parameters that I want to use, right, the input parameters. So the batch size I want 64, right, batch size of 64, epoch of 20, num class, or that's the number of classes to be 10, right, which is going to be the number of neurons in my last layer. Okay, and the number of neurons in my last layer is going to contain 10 over there, which is equal to the number of classes over there. Okay, all right, then once we have specified all this, I will start building my architecture. So I have the convolutional layer, then I have the fully connected layer. Okay, now inside the convolutional layer I start with the sequential. Okay, I initialize it here. I just name it as fashion underscore model, right? And then here I'm going to put in my conv2d over here, right, with 32 neurons over there, right? And the kernel size is 3 by 3, activation is linear, input shape is 28 by 28 by 1, padding equals same. Okay, meaning that add padding. If I do padding equals valid, it means that I don't want any padding. But if I do padding equals same, it means that I want padding to be there. Remember, we've learned padding in the previous tutorial, and I'm sure you have a good understanding of what padding is. Okay, where we surround the where we have our data, right? Let me just give you an overview of that one, just in case you want to refresh that one. So our input feature looks like this with some values over here. Okay, and then we'll put some filter on top of that. Later on we end up having small feature map. But if we want this size of the feature map, right, maybe here was 5 cross 5, and then here will end up becoming, say, 3 cross 3, right? But if we want 5, we want to be able to end up with another 5 cross 5 over here, then we need to pad this one. Okay, we need to pad this one with some zeros so that we will be able to get 5 cross 5 at the end. Okay, that's what I'm doing here. If I do padding equals same, it means that I want the size of this feature map to be the same as this input volume, or the image. Okay, if I do padding equals valid, then it means that I am okay with starting with 5 cross 5 input volume and ending up with 3 cross 3 feature map. Okay, so that's basically what you're doing over here, right? Then once I do that, I add some sort of non-linearity over here, which is nothing but the activation function, right? And here you can see that I'm using leaky relu. Okay, you can also try any of the other, right? Previously we've been using relu, but this one I want to change it and then try out leaky relu and see. Okay, all right, then after that I add max pooling, right? And then I add after that I add conv layer activation function, max pooling, right? Max pooling will come. Okay, then conv layer will come, then activation function will come, conv layer will come, then finally I flatten it, okay, before I feed it to the dense layer. Okay, so it's just you can see that it's just same process that I keep repeating. Okay, I have the input layer, which is conv layer. Okay, so conv layer here, then I have activation, then I have pooling. Okay, I have pooling over here, right? Then again I start with conv layer, I have activation, I have pooling, right? And then again I start with conv layer, I have activation, I have pooling. Okay, then finally I flatten it. So you can see that it's just repetition, right? It repeats around this. Okay, conv layer, activation, pooling, conv layer, activation, pooling, conv layer, activation, pooling. Okay, then I go to my fully connected layer. So inside the fully connected layer, I have my dense layer starting with 120 neurons over there. Activation equals linear, and I don't need to specify the input shape because it's already here. It can easily detect it, okay, and use the same thing. But if you are building only fully connected layer, then you need to specify. All right, if you're not building this one, then you need to specify it over here. Right, then here I'm adding activation. Okay, adding activation, and then finally I'm adding my dense layer. That's my final layer with my number of classes over there, which is gonna be 10 classes. Okay, and then activation for classification of multi variables is going to be softmax. Okay, that's basically what is happening over here. Right now, once that is done, the next thing is to compile it. Okay, so if you see here, I have my fashion model, fashion underscore model, compile, and then the loss here is I'm using categorical cross entropy. Okay, and then the optimizer I'm using Adam, right, and then the matrix I'm using accuracy. Right now, once that is done, I mean fashion model dot summary, and this is what we have. Okay, this is what we have as the summary over here. So if you see the summary, you can see that we have the first input over here, right? That is the first input. You can see that 28 cross 28, and then 32 neurons over there with which will end up with 320 parameters. Okay, if you want to see how these parameters are calculated, I've given you some. We have seen this one in the previous tutorial, and I'm sure by now you even know how to do this, right? But if you want to know, I've actually given you how it is done. So we have 3x3 filter over there. Okay, 3x3 filter over there, and the channel is 1. Okay, we have one channel that we are putting. Okay, if you go to here, right, we have 3x3 filter, right, filter size, and then our channel here is 1. Okay, and then we have our input neurons, or the number of channels that we're going to specify to be 32. Okay, so that's what is happening, right? 3x3 filter with the channel to be 1. If it is say a colored image, then this channel is gonna be 3. Okay, but this one is a gray image, so this one is 1. Okay, plus 1 is just always there as bias that we just add. Okay, so if you calculate this one, you're gonna have 320, right? And that is what is here. Okay, so if you want to know how this one also came about, okay, so here you can see that now what is coming in to here, right? What is coming, remember here is just this one, so that's why there's no parameter there, because here is just activation and max pooling, so there will be no parameter to learn. Okay, the parameters that we consider is only happening when there's a conv layer. Okay, when there's conv layer, that's when there will be parameters. Okay, but when there's pooling and activation, there will be no parameters in there. Okay, pooling and activation, you see that there's no parameters. Okay, pooling and activation, you see the flatten activation, pooling, there will be no parameters, right? It's only when it is conv layer or it is dense layer. Okay, conv layer or dense layer, that's when you see that there will be parameters. Okay, so if you want to see how this one also came about, okay, now what is coming in here, right? Initially it was 28 by 28 by 1. Okay, so that's why here we're having the channel here to be 1 and then adding bias to it. But now you can see what is coming in here is 28 by 28 by 32. Okay, so here instead of 1 you're going to put 32 over there, right? 32, and then you can see that here here you can see that we have 64 channels over here, right? So instead of 32, right, instead of 32 here will be 64, right? And if we run this one, you see that we have 18,496. Okay, 18,496. In the same way you can do it for this one, right? So here what is coming in is 64. So instead of 32 over here, we put 64 over there, right? And if you go over there, right, we have 128 over there, right? So you put it over here, 128 over there, right? 128. So if we do that, you see that we have 73,856. That's what it's here. Okay, you can do the same thing for all the others, right? So that's how you calculate it. Okay, now if we plot the sequence of what we have done, okay, of our architecture, right, this is how it looks like. So we are coming in with 28 by 28 image, okay, and then 28 by 28 image. That's what we're going to feed to the the conv layer, right, the first conv layer. All right, and that is going to generate 28 by 28 by 32 different feature maps. Okay, and then we feed that feature map. Okay, we feed that feature map over here to the rel, which is the activation function. That is not going to do anything to it, so you can see that it's just repeating the same thing over there. Okay, and the max pooling is also not going to do much. It's just going to pull the maximum, right, the maximum file over there, and then you see that this 28 by 28 will be half of it. Okay, because it's going to be doing only the maximum, so it's just going to reduce it to half, right? If we have it something like this, right, if we have something like this, right, where we have maybe here to be on 814, right, and then here to, like we saw in the when we're dealing with the theoretical concept. Okay, so we're going to select the maximum. If we select the maximum from here, it's just going to come up as just one box. If you select the maximum from this this 4 cells also, it's also going to come up with another box. Okay, if you select the maximum from this entire 4 over here too, it's also going to come up with one of them. Okay, if we select the maximum from the last box over here, it's also going to come up with 1. So it's going to reduce this one. This one was 1 2 3 4, and this one you can see that it's just 2. It's 2. So here was 4 cross 4, and it will reduce it to say 2 cross 2. So whatever it is, right, 28 by 28 is going to reduce it to 14 by 14, which is half of it if you apply max pooling. All right. And then the same way over here, you can see that in the conv layer, we feed this one to the conv layer. Okay, and what is going to happen, that the size is going to be the same, but the feature map, right, the feature map is going to be double. Okay, the feature map is going to be double, and then we feed that to the next one. Okay, we feed that to the next one, and the same way here is just in activation function, so nothing will happen. Okay, if the activation function, nothing happens over there, right? We don't do anything to the parameters, and then we add max pooling. So if we're having 14, right, half of it is going to be 7. Okay, the max pooling will reduce everything to half, right? And then this one will remain the same thing. Okay, and then you can see over here as well, right, 7 over here, right, 7, right. If we feed this one to the next convolutional layer, right, we will have the same thing, and then this one is going to increase, right, and then we do another activation, which is not going to do anything on it. Okay, just going to maintain it like that, and we do another max pooling on top. Okay, another max pooling on top. So if we do another max pooling on top, 7 is going to reduce to half of it, right? Ideally 7 divided by 2, right? 7 divided by 2 is supposed to give you 3.5, right? But we cannot have that 3.5 over here. It's not acceptable in max pooling, so it's gonna run off to 4. Okay, it's gonna run off to 4. So that's what run up to 4. Okay, it's gonna run it up to 4. So that's why you see 4 over here, right? Then we feed it to the flatten, right? We flatten that one from this 4 cross 4 cross 128 to this long 2048. So it's just like this, right? This how it's gonna be like, right? If I should maybe calculate that one for you to see. So it's going to be 4, right? It's 4 cross 4 cross 128. Okay, I'm just doing this one, how we do the flatten to get this 2048. Okay, now if we do that one, you see that we have 2048 over there. That's how it's gonna do. Okay, so now we have one long, right, instead of having say like this, right, 4 cross 4, right, and then we have 128 of these 4 cross 4s. Okay, 128 of these 4 cross 4s. Okay, instead of having it all this one, we just flatten it out. So we're just gonna have one long, right, one long 2048 of that. Okay, one long 2048 of that. So it's gonna be 2048, right, cross 1. Okay, just only one, one column with 2048 rows, right? That's going to be the data points we're going to feed into our neuron. Okay, our fully connected neuron. Okay, so that's what we're going to do. So once that is done, once we have flattened it, we feed it to our dense layer, which is our fully connected layer. Okay, we feed it like that, and then we're gonna come up with 128, right? Remember here we're going to do some weight multiplied by the data points that are here. Okay, and then we apply some sort of activation function on it. Okay, so this x multiplied by this y, which is nothing but the data points over there, multiplied by the weight. It's either we are going to allow it to be activated to the next neuron or not. Okay, so depending on the activation function that we are using over there, which in this case is rel. Okay, so that is going to determine, and then we will end up allowing 128 of them to get out. Okay, 128 of them to get out, and that's what that 128 is what we're going to use to predict our 10 class finally. Okay, so I hope now you get an idea of how what is happening over here, right? So you can see over here that if I should summarize, you see that when it is conv layer, we have these ones to be maintained. Okay, we have these ones to be maintained. Only this one changes, right? That's the feature map. Okay, that's what it changes. If it is activation function, right, if it is conv layer, these ones maintain, and then the feature map changes, right? If it is activation, nothing happens. Okay, if it is max pooling, then these two also changes, right? But this one also remains the same. Okay, if it is conv layer, these two remains the same, right? Only this one changes. Okay, that's how it is. So you can just, take your time and then examine like that. All right, now let's go to where we actually fit the model. Okay, now we have compiled the model, right? We have defined our architecture, we have compiled the model. Now let's fit it. So this one is going to take quite a lot of time to run. That's why I'm not running the notebook, because it's going to make the video very, very long. All right, and I don't think it's wise to do that, but at your own time you can do that. Okay, you can run the code and you see it takes some couple of time, but you have to wait for it to do it. Okay, so I have my train X, and then I have my my train labels, and my batch size, epochs that I want to use, my validation data, right? And then I've run this one 20 epochs, right? So if we see the evaluation part, right? This is the error that I got on the test, right? 0.5, and it's quite okay, and the test accuracy is somewhere around 0.9, right? The 0.91 or 92 approximately, right? 92%. Okay, what I'm going to do next, right? Let me go down here, right? That I want to plot this thing for you to see how it is doing, right? I want to plot them so that you can compare the training and validation accuracy, right? So that's what I'm doing, right? And here you can see that I'm doing accuracy, and in accuracy I'm using my fashion underscore train, right? And then I'm getting the history, right? Inside the history I'm selecting accuracy, because if you do this, right, if you do fashion underscore train dot history, you'll be able to see the accuracy, all the accuracies that you were having, okay, and all the loss that you were having. Okay, and then you're also going to see all the validation accuracy, right, and all the validation loss. Okay, so I want to plot the validation accuracy as against the training accuracy, and also the validation loss as against the training loss. That's what I'm doing over here. So here I'm selecting the training accuracy, then I'm also selecting the validation accuracy, then I'm selecting the training loss, then I'm also selecting the training accuracy. Okay, then finally I will do the plotting over here, right? Plt.plot, right, as against the epochs, and which the epochs is nothing but the length of the number of accuracies that we have over there. Okay, all right, then here is just plotting, right? I'm just labeling it as training accuracy. Okay, as you can see, that's the the key that I have: training accuracy and validation accuracy. That's what I'm putting on top of this plot that I have, and then the title is going to be training and validation accuracy, as you can see. Okay, and then I'm setting I'm creating these ones as well, right? The loss as well, so it's just two of them, right? One for the accuracy and one for the loss. Okay, one for the loss. Okay, that's what I'm doing. So if I should separate this one a bit, right, you can actually see it. So one for this one is for the loss, this one is for the accuracy. Okay, now if you study it very well, you can see that we have in this case we have the training accuracy to be very, very high, whilst the validation accuracy gets saturated somewhere, right? It gets stagnant, not moving that much. Okay, it's just plummeting over here, just saturating like that. Okay, but ideally I want the validation accuracy to also rise as the training accuracy is rising, but we can see that it's not the case. So if we see the errors, it's quite the opposite. You can see that the validation loss, right, the validation loss, which is the dotted one, is very, very low, and it should be low. If the accuracy is very high, then the loss should be very, very low, right? And here you can see that the validation accuracy is not that high, so the validation loss is very high. Okay, if the accuracy is not high, the loss will be high. If the accuracy is high, the loss will be low. Okay, it's as simple as that. Okay, it's as simple as that. Let me summarize it for you. If you have the accuracy to be high, okay, if the accuracy is high, okay, if you have the accuracy to be very high, it means that the loss, right, the loss of that will be very low. Okay, in the same way, if you have the accuracy, right, if you have the accuracy to be low, right, if you have the accuracy to be low, then you expect the loss, okay, you expect the loss to be high. So it's just the opposite. If this one is low, this one will be high. If this one is high, this one will be low. Okay, that's how you see it over here. You can see that the gap is always wide, but we don't want it this way. We don't want the gap to be wide. right? We want here, what we want is that we want all of them to be low over here. That's the loss. And here we want all of them to be high over here. That's the accuracy. We want all of them to have high accuracy, but that's not the case in this scenario. We have the accuracy here, one of them to be very low, and here you can see that the loss of that to be very high. And our main concern is even this one, the validation. So if the validation is performing poorly, then we need to do something. Okay, so what we're going to do next is we're going to add a dropout in our architecture and then see how the performance is going to be like. Okay, so in the same way, I'm running 64 batches with epochs of 20 and number of classes to be 10, just like we did earlier on. Now if we come to the architecture, now this time I'm going to add some sort of a pooling over here, I mean a dropout over here. Okay, so you can see that I'm adding some dropout, right? I'm adding some dropout inside. Okay, I'm adding some dropout inside. So here I'm adding 25% dropout, right? Here I'm adding 25% dropout, and here I'm adding 40% dropout. Okay, over here. All right, but I mean initially when we designed the architecture, we're not having any dropout inside. If you see it over here, right, there were no dropout in. Okay, there were no dropout. Now I'm adding dropout so that I'll be able to I mean curtail this overfitting, right? It's overfitting because the training accuracy is very high, but validation accuracy is not that high. And the loss too, you can see that the loss here is very low, but this loss is very high. So we need to find a way to reduce it. Okay, that's why I'm adding dropout over here, right? And inside the fully connected layer 2, I'm adding one dropout over here. Okay, now if we do that and we rerun this model, okay, if you go the way down here and see what we have, right? If you see the graph again, now this is what we want, right? This is the perfect one that we want. Okay, we want all the accuracies to be very high and we want all the losses to be very low. This is the perfect scenario, and this is what we want to do. Okay, so I mean if you do it and you see that, if you plot your graph and you see that it's not that doing good, right, you can feel free to add dropouts or I mean any other regularization I mean technique over there, like dropout or L2 regularizer over there. You can add those kind of things, and then you keep on tracking them to see, right, maybe reducing the number of epochs or something like that. Okay, just keep on manipulating it, and you're going to find the perfect I mean spot that you will stop. Okay, so I mean I hope this one you have learned quite a lot from this notebook. Okay, I hope you have gotten quite a lot of insight from this notebook. All right, so that is convolutional neural network, or ConvNet, for you, and I hope you have really enjoyed this notebook, and I urge you to just go through one more time to have more clarity of what we have done so far. Okay, and also don't forget to give a good rating and a good review to the course, right? And your comments and your questions at the Q&A session. Okay, I will see you there. All right, so see you in the next tutorial. Have a nice day.